Today we're going to talk about wind tunnel testing. And before we do, I'm going to try to set the stage by discussing the generalities of fixed wing aircraft in flight, which are essential to understanding why we do wind tunnel testing and why it's important. But in many cases, I will include things from my own family history. My grandfather was very active in Washington aviation during the 1930s, which is a very illustrious era of flight. And of course, the opening of this video showed the HARM missile, which I actually worked on. That was my first job at Texas Instruments. But today I'm going to use another rather more important event to illustrate some of the concepts that we have here, and that is the Wright brothers flight. On 17 December 1903, the Wright brothers flew the first successful fixed-wing aircraft flight in history, and they did so near Kitty Hawk, North Carolina. And as you can see from this panorama, what the panorama shows is the flight area where they actually accomplished this. And the last one was just from one end of the panorama to the other in just under a minute. They actually had 4 attempts on it. And we're going to see how many of the principles that we discuss in the wind tunnel test influenced the Wright brothers and their flight. Let's start by going back to Newton and some basic theory in terms of lift and drag. Now, of course, question you ask is why is that important? Well, basically, when we talk about fixed wing aircraft, we have 4 different factors we have to continue. Now, you can see those in the diagram. The first one is we have to have gravity. Gravity always wants to pull it back to Earth. Against that, we have to generate some way of lifting it. In other words, a force that opposes gravity. We normally do that by putting horizontal thrust or nearly horizontal thrust. Planes obviously don't fly horizontally all the time, so we have to, but in any event, the concept is the same. Opposing that is drag. We know instinctively if we stand in a high wind that there is a force exerted on us by the high wind, and that is a drag force. And that drag force is present not only with aircraft but with buildings and other structures, and design to that is very important in a successful building, particularly if they're your tall buildings. But when we look at drag, we wonder, wow, how large is that force? The first person to really tackle that issue, like he tackled so many other issues, was Sir Isaac Newton. And he came up with the formula you see on the screen. The formula basically is they have a cross-sectional area. Now, this is a source of confusion for students. The cross-sectional area of a aerodynamic object is in part determined by just looking at for obvious things, but sometimes it's strictly convention, and we actually have some discussion of that later on elsewhere in my monographs and whatnot. But basically, if you take for example, let's say that you had a sphere. Now, obviously a sphere is a 3-dimensional object, but an area is 2-dimensional. Basically what you would do is if you've got air flowing to the sphere this way, as you see in some of the diagrams we have, then we basically would cut an area through the sphere, and that would be the area that the airflow would see, quote unquote, as it passes over the sphere, or the teardrop, or whatever, or the plate, or whatever object we're putting into the wind. So that's the cross-sectional area for that. So basically for a sphere, it would be the area of the largest circle that you could cut through the sphere. In the case of an airfoil, it's a little different. because it's basically usually the planform area of the wing. And what I mean by planform, and I think my civil students may have a little bit better grasp on this, is that if you look down on the wing, there is an area you can see. You've got the leading edge in the front and the trailing edge in the back, and you've got an area, and you've got the wing tips and the fuselage, and all around those you have an area. And that area can be easy to measure, it can be tricky to measure, and in some cases some wings are configured to not to have or irregular, or to change that. And so in our case, we're going to use a rectangular airfoil, and we're going to basically say that the planform area is the chord, which is the distance from the leading edge to the trailing edge, times the span, which is the length of the wing. So that should clear that up for you. Of course, with the area out of the way, we have to look at the rest of the formula. Rho is the density of the fluid we're going through, and you know, it's when we say aerodynamics, you also have to consider that before aerodynamics we had hydrodynamics, where we measure the resistance of an object through the water. So we have both, and U is the x-axis velocity of the air relative to the object. Now that's important, because you can have a situation where if the air is still, then whatever velocity the aircraft or the airfoil moves is the complete velocity. Whereas if the air is moving, then even if it's stationary, then that velocity becomes the velocity, the effective velocity of the for lift or drag purposes. Now, I will mention the fact that one of the reasons why the Wright brothers went to the Kitty Hawk area was because, like virtually any other seaside place, you've always got a wind blowing off of the ocean. And if you can point the aircraft into that wind, then you've got some velocity going for you, and that will create the lift and the drag. As we'll, well, more importantly, the lift. The drag we have to deal with, but the lift, as we will see. Well, once Newton laid that, and you know, and then there's the constant, some constant. As you can see from the diagram I'm putting back up, what that constant might be depends on the shape of the object, and that's something you're going to deal with in the wind tunnel test. The problem that you have, however, is what C is. Well, there were some, you know, if all flow was laminar, then that would be a fairly simple proposition. The problem is all flow is not laminar, and you have situations where you're having to deal with it in turbulent. Once you get into turbulent flow, then the airflow becomes complicated. One thing that complicates is the issue of viscosity. However, we discussed earlier in the viscosity test, we talked about inviscid flow and how inviscid flow is an idealization of real flow. Well, in the 18th century, people thought about, you know, inviscid flows, that maybe if we could just get away with inviscid flow, we could get further down the road in our search for a solution to this problem. And that was terrific. And what that involves is we take Bernoulli's equation and we extend it, which is an inviscid equation, by the way, and we apply law. As you remember in the flow bench, we apply losses in some interesting ways, but it's basically an inviscid type of equation. And then if we extend that to a two or three dimensional continuum instead of just a linear type of thing, one dimensional, then we have a situation where the then we went to the point we have Euler's equation. The only problem with this, the thing that really put the brakes on this, was Jean-Laurent D'Alembert, who came up with D'Alembert's solution of the wave equation, pointed out his famous paradox. His paradox basically said that for a symmetric object, and if you do not include the effect of viscosity, then the drag on that object is basically zero. And that kind of put things back, because if you start getting away from D'Alembert's approach and start getting into, if you get away from an inviscid approach, viscosity complicates things. You go from the Euler's equations to the Navier-Stokes equations, and things get more complicated. And that has been one of the major challenges in computational fluid dynamics to this day. So that set people back. But as the 19th century progressed, people started to do it. Saint-Venant has had some very insights. In fact, he came up with, in some ways, with Navier-Stokes equation before they did. But in any event, they decided. So as things progressed, people began to realize that analytical solutions to this particular problem were going to be hard to come by, at least by the computational power of the 19th century. So we start turning to experimental. And then we run into the next problem in flight. One thing I'll mention before I go on is that all we're going to deal with this experiment and with our other aerodynamic experiment, the propeller experiment, is the simple fact that this is all subsonic flight. That's all we're going to deal with. We're not going to get into the complexities of shock and supersonic. And by the way, just as a matter of definition, subsonic flight takes place, obviously, when the airspeed is less than the speed of sound. And so therefore the Mach number, which is the ratio of the airspeed to the speed of sound, is less than unity. And we're going to keep our speeds low in this experiment. And it's interesting to note that, for all the interest in hypersonic flight today, the other on that end, there's quite a bit in a sense hypersonic flight, but also on the other end, we have drones. Now, the difference between drones and fixed aircraft is really very simple. In fixed aircraft, we put the aircraft with velocity in order to generate lift using the airfoils in order to go against gravity. With drones, we simply point the propeller in a vertical direction and actually do the thrust directly against gravity. And we're going to talk about how the propellers do that when we get to the propeller experiment. In the meanwhile, let's talk about drag. Now, after some experimentation, and the convention settled down, the drag is equal to the equation you see on the screen. It is very similar to Newton's equation. There's only really two differences. One of them is they divided it by 2, which basically turns u squared over 2 into an energy type of component. And the other one is you got c sub d. You put a d subscripts there. That means that we're only considering with that the drag. If we were able to put an object into an airstream, and we could measure the force, then we could, and we know the area and the density of the air and the airspeed, we can compute the coefficient of drag. Obviously, the higher the coefficient of drag, the higher the coefficient of drag, the higher the drag force, and vice versa. The lower the coefficient of drag, the lower the drag force. Obviously, in virtually any moving object, the one thing we want to do is to reduce the coefficient of drag. And one way we do it is to streamline an object, where we try to eliminate the trailing effects of the abrupt end of the object by smoothing out the end. And we're actually going to see this in the wind tunnel when we compare the spherical object with the teardrop object. So the drag coefficient is important, and we can define drag coefficients for lots of things. Buildings, automobiles, they're constantly measuring and trying to improve the drag coefficient of automobiles in order to reduce the fuel consumption and actually improve the performance of the vehicle. So we have that. The other thing is obviously the lift coefficient. As we put airfoils through the air, we get differential pressure, and there's a couple of ways that happens. One of them would be if the airfoil is not symmetric. In other words, that the lower surface of the airfoil is different than the upper, usually a little bit more concave, say, than the upper, like in your classic Clark Y airfoils. In that case, what happens there is that the pressure under the wing is greater than that over the wing because of energy changes taking place in the airstream above and below, and as a result of that you have lift. Now lift, the equation, as you can see, is identical to the drag, except that the only difference is that the coefficient is different, and we measure different. Instead of measuring the horizontal force like we do with drag, in the lift we measure the vertical force, because we're interested in seeing how much vertical force we can generate with an airfoil and keep the aircraft aloft. And that would be its lift coefficient. And we're going to measure both of those with an airfoil. Now, I said that one way of getting lift would be assuming that the airstream goes through the center of the airfoil. In other words, that there's no angle between the airfoil and the airstream. But the airfoil that we're going to use is the classic NACA 0012. It's symmetric about that. And so therefore the only way and as we said, there's no lift generation because there's no difference in the airflow above and below. So what happens? Well, what happens is that we have to basically angle the airfoil against the we angle the airfoil versus the flow, and that angle is called the angle of attack. And as we increase the angle of attack, the lift coefficient will increase, the lift force increases up to a point, and we reach the stall mode. Now the diagram you see shows about a 15 degree. That's not a hard and fast rule. That's a ballpark figure. One of the things you need to determine with the NACA 0012 airfoil that we test in our wind tunnel, one is the actual where that stall takes place. What will happen is that when you reach the lift coefficient will keep going up, you will hit the stall, and then the lift coefficient will start going down. Now, if you experience that in actual flight, the result is usually not a good one, because once you lose lift, your aircraft will start to drop. If you lose a lot of lift, your aircraft, unless you can find a way of restoring it, you will lose a lot of lift, and your aircraft will meet the ground in a very unpleasant way. So it's important to understand stalling, and many aircraft crashes have taken place because the airfoils have basically stalled. Now we can resume with discussion of the Wright brothers. The aerodynamic laws were beginning to be understood decently well, at least from a theoretical standpoint, by the time the Wright brothers began to experiment. Neither one of them was were engineers as we would understand it. So much of what they were doing was trial and error. And the truth of the matter is that much of what everybody else was doing was trial and error, because they were not quite able to marry the theoretical to the practical as well as they would have liked. So they had to do a lot of experimentation of that kind. Full-scale experimentation is not only, and they started with gliders, then they got towards powered air, but they were having difficulty keeping their stuff in the air. And in many cases, mistakes like that were fatal, not to them, but to many of their counterparts. So they had to come up with a way of getting around that problem so that they would live for the next flight, and that they would actually learn something and move on down the road or through the skies. The turning point, the whole Wright brothers experimental sequence is complicated, but the turning point was, in fact, their wind tunnel. Now, their wind tunnel, which I've showing on the screen now, is not that, in terms of the throat area of the wind tunnel, is not that much bigger, if at all bigger, than ours. They're about the same size. The biggest difference between the two is the fact that our wind tunnel is much longer, because it is trying to put an even, uniform velocity airflow through the throat. And they do that by putting the fan, which is pulling the air through, as far away as they can. So therefore, our wind tunnel is much longer than the Wright brothers. Nevertheless, that is the same. They had ways of measuring the lift and the drag, and by doing experimentation on similarly shaped objects, they were able to come up with airfoil shapes and were able to estimate what it would take to generate enough lift to keep the plane aloft. Now, the obvious question is, what gave them the right, so to speak, or maybe what enabled them is probably more to do that. Why could they say, well, we can do this in a small wind tunnel and then we can turn around and expand it? The answer to that, or why did wind tunnels in general work? Because all wind tunnels work that way. They all have the same, pretty much the same idea, that you take a small object, you test it in a wind tunnel, then you extrapolate it. How does extrapolation work? The extrapolation works, and I'll leave it more towards the theory and lecture course to explain this in more detail, is something called dynamic similarity. And basically, if we can establish some type of relationship between small objects and large objects, then we can actually design tests with small objects and use that to educate ourselves with the large objects. Dynamic similarity in its simplest form is done through dimensionless quantities. And the dimensionless quantity we're going to concentrate on with this wind tunnel is the Reynolds number. The Reynolds number, in my monograph on this subject, goes to a nice little derivation, is basically an expression of the inertial force versus the frictional force. The frictional force mostly coming from the viscosity of the fluid. And basically, that relationship, say for example, it reduces it to a very simple between the velocity, the diameter of the object, or the basic size of the object, and the density over the viscosity of the fluid. And if we can come up with an airfoil that has a Reynolds number in the small, if we can upscale it to the same Reynolds number as large, we will get similar results. That's the idea. That's why the Reynolds number is so important. Osborne Reynolds had come up with it about the mid 1880s, I believe, in that era. So the concept was known to the Wright brothers, even if it wasn't fully fleshed out as it is now, or even later on in the 1920s and 30s. So that's why the Reynolds number is important. Now, if you look at that number carefully, you will realize that in order to take full advantage of it, you have to control more than the velocity and the diameter. You have to be able to control the density and the viscosity of the air, and that's done by controlling the pressure of the air. The Wright brothers wind tunnel, and for that matter our wind tunnel, are open wind tunnels, and they don't give you much. But nevertheless, what we want to do is to use the Reynolds number as the basis. In other words, I will ask you to plot the drag coefficients and against the Reynolds number, because for a drag coefficient we vary the speed of the air, and we compute the and from there we compute the drag. We can get the lift force, and we compute the drag coefficient, and those results can be extrapolated somewhat. And I say somewhat because our wind tunnel, let's just be honest, is not the most accurate thing. We can extrapolate those results to larger spheres. With airfoil, it's a little more complicated, but they're given in my monograph, I give you. Of course, for one thing, with lift coefficients, we normally don't compute we normally don't vary we basically run at a certain airspeed, which means we fix the Reynolds number and we vary the angle of attack. And we do this for, in our case, 2 airspeeds. And when we do that, we can see just exactly what the effect of Reynolds numbers, at least for 2 airspeeds, is on the stall angle and on the lift coefficient itself. And we can also compare those and see how much difference it'd be if we were able to really increase the airspeed beyond what our wind tunnel is capable of. And I've got some figures for much higher for that particular relationships at much higher Reynolds numbers than we have in our wind tunnel. Also, one thing that I urge all of my students to do is to be careful in computing your Reynolds numbers. I've got quite a bit of material on my website on how to do that, and your fluid mechanics book will likewise. The biggest problem I see with Reynolds numbers is the units. They can really trip you up very, very easily. So take my advice. I'll also mention that the Reynolds number is not the only game in town in terms of number. It's just the one we use mostly with aircraft. The Froude number, which we looked at in the hydraulic jump experiment, is actually the ratio of the inertial force to the gravity force, and we use that more with ships than we do with the Reynolds number. In this wind tunnel experiment, we're going to test 3 objects. They're the 2 drag objects and the lift object. The drag object, we vary the speed according to what you see in the data spreadsheet, and you simply vary it up and down, or you can go either way. Actually, you can start from the top and go down, start from the bottom, go up, or if you want 2 sets of data, you can make a round trip. Particularly if you have suspicions about it. And the third one is the airfoil, which we test both lift and drag. We pick 2 speeds, which are given in the data spreadsheet, and we measure the lift and the drag at various angles of attack up into an angle of attack which is just past the stall. And just as a hint of what that might be, if you look at the diagram, it says about 15 degrees. You need to probably get past that to really be sure that you're past stall. A lot of students is tempting to give up too early, and that's not a good thing, because if you miss the stall, you've missed a lot of the experiment. There are a couple of things about wind tunnel testing that you need to be aware of. There are two things you have to watch for. One of them is a thing called tear. And the problem is with tear, you'll notice that our wind tunnel has a stand. And the objects are affixed to that stand. That stand does have some effect on the performance of it. And in fact, you may notice that there are differences between what you get and what you see in the literature. And some of that, at least, is due to that tear. So that's important. Many times, more sophisticated wind tunnels will use very small cables in order to transmit the force to measure it properly. So you need to be aware that of that as you proceed in the experiment. The other thing is interference. We talk about free flow. Now, free flow theoretically means that the velocity is the same not only at the axis or where the object is, but at an infinite distance therefore. Well, we all know that that's really not true. In a wind tunnel where we have a constrained area, we have a fixed area surrounded by that plexiglass tube that we have, we really don't have one. And if the object is too large, then the sides will start interfering, so to speak, and screw the data up. We have tried to reduce the size of objects, and we've had problems with this in the past, to minimize interference. The objects that we have chosen are designed so that they are small enough to avoid having interference, but they're large enough to try to overcome some of the effects of the stand or the tear. So they're kind of trapped between the two. But in analyzing your results, you should take both of those into consideration. The dimensions of all the objects are given in one chart right before the beginning of the actual video portion of the experiment. Right now, right at the end of this lecture, you'll get the dimensions for all of the objects that we test, all three of them. One thing you should also note is that for the two drag objects, the Reynolds numbers, you need to look at the Reynolds numbers will not be the same for a given airspeed. You need to figure out why that is and plot it accordingly. I see many times that students will just assume that they're the same. They are not. And you need to find out why, even if the airspeed is the same. And it's fairly obvious if you look at the Reynolds number itself. So, in any event, with all that, let's go ahead to the lab and proceed with our experiment. This is the wind tunnel we'll be using. It's an open wind tunnel. The end you're looking at is the intake end where it brings the air in from just simply the outside. It's not pressurized in any way. Once it gets in, we measure the velocity using this pitot-static tube, which I'm focusing on right here. Whatever we're testing is mounted in the stand. That's an airfoil. I'll talk about that in just a minute. And it's mounted in that stand, and below it are two things. At the very bottom is the mechanism used to measure the force of lift and the force of drag. The force of lift being, of course, the vertical force, and the force of drag being the horizontal force. You'll also notice that there's a little indicator here. I'm kind of coming at it backwards, but that's the angle of attack indicator. You can actually adjust the angle of attack. Currently, the angle of attack is set at 0. And then you have the control system for the wind tunnel. It's fairly old. And the power supply for that control system. And we have in the back here the exhaust. Actually, the fan pulls air through the wind tunnel and then it exhausts out this way. So you don't want to be standing here during the operation of the tunnel. Over here is the computer. We do have a computerized control for this wind tunnel, but that's about it. Here in the front, and you're going to be seeing a lot of this in just a few minutes, is the lift and drag. The airspeed doesn't really work anymore. Lift and drag. Those are the lift in pounds and the drag in pounds that are being exerted on the stand. So that, in a nutshell, is the wind tunnel. And we mount the object securely on the stand. The object that is currently in the stand is, and the one we're going to start with first, is a NACA 0012 airfoil. And I'll give the dimensions of that airfoil elsewhere. And you can determine the area and all in that. And of course the diameter, the quote-unquote diameter, to be more accurate. This airfoil is a probably the most analyzed airfoil shape in existence. It's very common to analyze this in CFD. My monograph wind tunnel testing has some extensive data on the subject. What we're going to do with this is the following. We're going to, with an airfoil like this, the way we do it is we pick a couple of speeds, and I'll tell you what those speeds are when we get up to them. And what we're going to do is we're going to vary that angle of attack, which you see is currently set at 0. And we're going to vary it one direction. Because it's a symmetric airfoil, we don't really need and wouldn't get a lot out of varying it in two directions. Once we do that, then we can, from there, we'll take and break down the data. And we'll analyze the lift and the drag for a variety of angles of attack for two different airspeeds. Alright, now I've turned the wind tunnel on. You can see the little streamers on the back of the airfoil vibrating. That's because of the air. My current airspeed is about 25.7 miles an hour. Now, because of the way that you probably noticed I had to look over this panel in order to get to the angle of attack. And basically, because the most important thing for you to do is to properly read the gauges, what I'm going to do is I'm going to announce the airspeed. I've already done that. I'm going to announce the angle of attack, and you can take the data as I actually gather it. So let me go ahead and work on the first one. Currently we are at 0 angle of attack. Okay, now we're at 2 degrees angle of attack. Let me see if I can get a little bit easier way to do this. Okay, now we're at 4 degrees angle of attack. Now we're at 6 degrees angle of attack. You can actually see the airfoil angling upward, which is what it's supposed to do. The angle of attack, of course, is the angle between the airstream, which is essentially horizontal, and the airfoil, which right at the moment isn't. We're at 8 degrees angle of attack now. And 10 degrees angle of attack. I'm at 12 degrees angle of attack. Degrees angle of attack. You see already that the streamers are beginning to react. You're starting to probably see some evidence of stall. And let me just go to 16, and this is 16 degrees angle of attack. Now what I'm going to do to save a little time, and actually do this in the lab, is increase the airspeed to about 45 miles an hour. The airspeed is about 46.8 miles an hour. 16. We'll start going down to 14. 12 degrees angle of attack. 10 degrees angle of attack. 8 degrees angle of attack. 6 degrees angle of attack. 4 degrees angle of attack. 2 degrees angle of attack. But certainly not least 0 degrees angle of attack. Again, this is taken at about parallel 47.5 miles an hour. So we're looking at some proper wind power. Now we're going to check the drag of a sphere. The sphere is loaded in the wind tunnel. As you can see, the drag is set to 0 for 0 miles an hour. What I'm going to do is I'm going to increase the speed up to about 50 miles an hour. And while I'm doing that, I'm going to tell you what the airspeed is, and you can see the drag speed for yourself on the gauge below. So let's go ahead and get started with this. The first airspeed is 18.8 miles an hour. This airspeed is 25.6 miles an hour. This airspeed is 32.2 miles an hour. is 38.4 miles an hour. This airspeed is 41.2 miles an hour. This is about 47 miles an hour. The reason why they have such odd values is because you dial in one airspeed and you end up getting another one. The last object we're going to test is this streamlined sphere. The diameter for it will be given for you either in the description of YouTube, the comments in my website, or wherever, but you'll find it. In any event, it is, again, the diameter being the diameter at the largest diameter of it. Basically, it's a sphere, but it's been streamlined. And the purpose of testing this is for you to compare it with the other sphere. Now, the only way you can, the two are not the same diameter. The only way you can compare the two and come up with a reasonable result is use dynamic similarity, i.e., what you'll need to do is to plot them on the same graph with Reynolds numbers versus drag coefficient and compare it to and see the effect of the streamlining. So let's go ahead and get the collected data. The first airspeed is 18.9 miles an hour. The second airspeed is 25.9 miles an hour. The third airspeed is 32.4 miles an hour. And that's the data for that shape. That should conclude our experiment. As always, thanks for watching, and God bless.